one more video in this section. But before I spend too much of your time, because that last video was way too long, I want to be really clear. You do not need to watch this video. This is purely bonus material. It's super interesting. You might want to give it a try, but you'd never be tested on it, and it's beyond anything that you should need to do for our class. At the end of the last video, I got into this idea of using infinitely many rectangles to calculate, not estimate, the area underneath the curve. In this video, I'm going to show you how. It involves some pretty advanced topics, and one of those topics I'm not even going to prove to you. I'm just going to ask you to trust me that this formula that can be written this way in sigma notation, but I'm going to assume you're not familiar with sigma notation, so I'm going to write it this way, is true. That if you're adding up a bunch of squares of consecutive whole numbers, there's a formula for how much that sum is equal to. And it's given right here. It's n times n plus 1 times 2n plus 1 over 6. What am I talking about? Let me show you the case where n equals 4. If n equals 4, then my sum on the left doesn't go up to n squared, it only goes up to 4 squared. So I got 1 squared plus 2 squared plus 3 squared plus 4 squared. So this is what? 1 plus 4 plus 9 plus 16. So 1 plus 4 plus 9 plus 16 is 20 plus 10, it's 30. But what if you didn't want to add up all those numbers and calculate it was 30? Or what if n was like 100 and then it was going to be really hard to add up all these numbers? Well, you don't need to add up 4 different terms. There's a formula that tells you the sum from 1 squared up to 4 squared that we calculated down here, and it's written on this side. All you have to do is take 4 and multiply it by 5, 4 plus 1, and multiply it by 9, 2 times 4 plus 1, and then divide that whole thing by 6. No way, that really works? Well, let's see. 4 times 5 is 20, and 20 times 9 is 180, and 180 divided by 6, sure enough, is equal to 30. And there's nothing special about 4. I just proved the case where n is equal to 4. This holds for any n, so it's kind of wild. If you were trying to, like, I don't know, keep some kid really busy, and you were like, add up the first 10 square numbers, so 1 squared plus 2 squared plus 3 squared all the way up to 10 squared. They could work on that for a little while, write down a bunch of numbers and add them all up. You could check their answer super easily. It would just be 10 times 11 times 21 divided by 6, whatever that's equal to. Anyways, trust me, this is a formula and it's true, and it's going to be the key to figuring out the exact area underneath this curve. How are we going to use this? Well, we're going to have to use limits, but it's not as bad as it seems. Ignore this limit for now. Eventually, what we're going to do is look at the limit as n approaches infinity. But don't worry about that for now. Right now, just think about what we want to do is draw rectangles that span from 0 to 4, like we've been doing in the previous video. And you're like, oh yeah, I got that. We did that with 4 rectangles. We did that with 8 rectangles. I can do that with as many rectangles as you want. How many do you want? And I'm like, I want n rectangles. And you're like, ooh, I was kind of expecting a number, not a letter. Okay, that's fair. But think n is some really, really large number. So like if n were 100, for example, it might help you to picture that. I'd want to divide this length from 0 to 4 up into 100 little segments. They'd all be super duper small. Let's see, I guess each one would be 1/100th of this length. I take this 4 and subtract this 0 to figure out how much of a horizontal distance I'm trying to cover. And then I divide that by the number of rectangles that I want. So I divide that by 100. The width of each rectangle would be 4 over 100. But I don't want 100 rectangles. I want n rectangles. But that's fine. I'm still trying to cover from 0 to 4. So I'm still covering a horizontal distance of 4. It's just now each of the n rectangles will have a width of 4 divided by n. So I can't draw these because I don't know what n is equal to, but picture a bunch of really, really, really small rectangles, and the width of these rectangles is 4 over n. If I could figure out the height of these rectangles, I'd be done, because I need to know the area of the rectangles, and the area of a rectangle is just the width times the height. So what is the height? You're like, ooh, wait a minute, it depends. If we're using left endpoint approximation, I'm going to use the left endpoint of each of these rectangles. And if we're using right endpoint approximation, I'm going to use the right endpoint of each of these rectangles. So which one are we using? Well, it turns out it doesn't matter. Because what we're going to do is let n get infinitely large. We're going to pack infinitely many rectangles in here. And so each rectangle will be infinitely thin, and if they're infinitely thin, the left endpoint and the right endpoint are right on top of each other. It doesn't make a difference. But for the sake of our formula, even though it doesn't matter at all, I'm going to use right endpoint approximation. So to figure out the height of this first rectangle, I'm thinking about the height of the curve at this point right here. To figure out the height of the curve at any point, I just evaluate f of that point. So what point should I put in here? Well, whatever this x value is right here. Right, but what is this x value? Well, let's see. It's not quite 0. It's 0 plus 1 of the width of this rectangle. The width of each rectangle is 4 over n. So what I want to do to figure out the height of this first rectangle is I want to figure out the height of this point. The x value of this point is this 0 plus 1 of these 4 over n's. Didn't quite get that? Don't worry about it. Think about the second rectangle for a minute. I'll draw it over here with some finite width, even though really we're letting these get infinitely small. For this second rectangle, I'd be interested in this point right here. The width of the rectangle is still 4 over n. Each of the rectangles have the same width, but the height of the rectangle is the height of this point, and that's the tricky point. How do you figure out the height of this point? Well, I just take the x coordinate of this point and I put it into my function f. So the height of rectangle 2 is f of whatever this x coordinate is right here. What is this x coordinate? Well, it's kind of hard to talk about this x coordinate because we don't know how many rectangles we have, but what we can think of is we're starting at 0 here, and then we're stepping to the right the width of one of these rectangles to get to the red point, and then we're stepping to the right the width of a second one of these rectangles to get to this point. So it's the 0, the starting point, plus 2 of the width of these rectangles, these 4 over n's. And if I had a third rectangle, which I don't really want to draw, but I'm going to do it anyways, it would still have the exact same width, but to figure out its height, well, maybe you can see a little pattern here. It would be f of 0 plus 3 of these 4 over n's. 3 of the width of the rectangles gets me to this x value, and f of, because I want the y value. Just from looking at these 3 example rectangles, I think we can come up with an expression that exactly represents the area underneath this curve, and that's kind of cool. To figure out the area, we have to add up the area of each of the different rectangles. Remember, the area of a rectangle is the width times the height. The width of each of the rectangles is 4 over n. So for the first rectangle, I'm going to take that width, that 4 over n, and I'm going to multiply it by the height. The height is f of 4 over n. But that's not the total area underneath the curve. That's just the area of this first red rectangle. I now want to add in the area of this second rectangle, the one that's pictured in green. To do that, I need to figure out the area of this green rectangle. It's the width of the rectangle times the height of the rectangle. The width of the rectangle is still 4 over n. The height of the rectangle is f of 8 over n. Wait, where'd that 8 over n come from? It's 2 times 4 over n. Why 2 times 4 over n? Because I have to walk to the right twice, and the amount I'm walking to the right by is the width of the rectangle, which is 4 over n. One more for good measure, the third rectangle pictured in purple has a width of 4 over n and a height of f of 12 over n. 3 of the widths of the rectangles as pictured right here. This is not the total area underneath the curve, it's just these first 3 rectangles, so maybe I can put like plus dot 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 to indicate that we'd have to continue doing this all the way until we got to our very last rectangle. What would our very last rectangle look like? Well, it'd be super skinny, infinitely skinny. It would have the exact same width as all these other rectangles that we're using the expression 4 over n to represent. And then the height of this rectangle would be based on its right endpoint. Well, if it's the last rectangle that we can squeeze in here, its right endpoint is exactly 4. So what is its height? Well, its height is just f of this value 4. How am I getting to this value 4? I'm starting at 0 over here, and I'm adding up not 1 or 2 or 3 of these 4 over n's, but n of them, because n represents the number of rectangles I have. So n times 4 over n. The width of this last rectangle, just like the rest of these rectangles, is just 4 over n, and the height of this last rectangle would be f of n of these 4 over n's. So 4n over n, in other words, 4. This expression is really, really complicated, but if you can tie each of these terms back to a corresponding rectangle, one of these infinitely thin rectangles, then you're following the idea of what we're doing here. All that's left to do from here is a bunch of algebra and take advantage of this fact. Ignore the limit part for now. We'll deal with limits later on. Let's just evaluate what's inside these blue parentheses. You might notice that each of these different terms have a 4 over n in them. So I can factor out 4 over n from each of the different terms. What does that leave me with? Well, I'd have an f of 4 over n left over from my first term, and f of 8 over n left over from my second term, f of 12 over n left over from my third term, 16 over n from the fourth term, 20 over n from the fifth term, and so on, all the way until I got to f of 4, my very last term. A lot of letters floating around, so this is really intimidating to look at. Maybe we can get rid of one of those letters. This f of 4 over n, we don't have to leave this in function notation because we know the equation of this function is 3 minus 1/4 x squared. So because f of x equals 3 minus 1/4 x squared, f of 4 over n would be 3 minus 1/4 times 4 over n squared. Similarly, f of 8 over n would just be 3 minus 1/4 times 8 over n squared. And by that same logic, I could change f of 12 over n into 3 minus 1/4 times 12 over n squared. And I could do that for all of these terms, each of the n terms that I would have in here, until I get to the very end, the last term, where I would evaluate f of 4, and I would get 3 minus 1/4 times 4 squared. All right, if this isn't already crazy enough, here's where I'm really going to test the limits of your algebraic imagination. We have n different terms in here, right? The first one, second term, third one, a bunch that aren't pictured, and then the nth term. Each of those terms have a 3 in them. I'm just adding up a whole bunch of stuff. I can change the order that I'm adding those up. I could take this 3 in red and add to that this 3 in green, and add to that this 3 in purple, and then add the next 3 and the next 3 and the next 3 and the next one that aren't even pictured until I get all the way to this last 3 that's pictured in pink. And you're like, wait, but what happened to the negative 1/4 4 over n squared? I'm going to write that now. And then I'm going to have this negative 1/4 times 8 over n squared. And then I'm going to add to that this negative 1/4 times 12 over n squared. And then I'm going to add to that the next one and the next one and the next one that aren't pictured, all the way until I get to this very last one, the one in pink, the 1/4 times 4 squared. All right, we're getting pretty close to the punchline here. Think about what we have written here. A whole bunch of 3s. How many 3s? Well, one for each of the different terms, right? This 3, this 3, this 3, all the 3s that aren't pictured in this 3. How many terms are there? Well, there's a term for each of the different rectangles, right? I'm only showing some of them because of this dot, 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 but there's a term for each of the different rectangles. And we have n different rectangles, which is why they each have a width of 4 over n. So what I have are n of these 3s, 3 plus 3 plus 3 plus 3, n times. If you're adding up n 3s, you have 3n. Wait, what? Think about it. If you're adding up 5 3s, you have 3 times 5. If you're adding up 10 3s, you have 3 times 10. If you're adding up n 3s, you have 3 times n. The sum of all these 3s is just 3n. Whoa, that's kind of wild. Yeah, and it gets even crazier. For each of these terms that are left over, they each have some stuff in common. They're each negative and they each have a coefficient of 1/4. So I can factor out negative 1/4, and then what I would have left, let's see, in red, I'd have 4 over n squared. In green, I'd have 8 over n squared. Note that this is plus here because I'm factoring out the negative for this negative 1/4. From this purple term, I would have 12 over n squared. I'd have a bunch more terms until I finally got to this last one in pink, which would just be 4 squared left when I factored out the negative 1/4. Instead of writing this as 4 squared, I'm going to write it as 4n divided by n squared. Why? Okay, first of all, 4n over n is just the same as 4, right? You cancel out the n's. But by writing it this way, each of these terms look more similar. They each have a denominator of n, which will be useful in my next step. You're like, oh my God, there's a next step. When is this ever going to end? We're close. Trust me, if you've made it this far, it's worth your time to finish this. We're really close to the punchline. Just like I factored out negative 1/4 from each of these terms because they each had a negative 1/4 in them, what I'm going to do is factor out 4 over n squared from each of these terms because they each have a 4 over n squared in them. And you're like, whoa, wait, what would that look like? Well, okay, from this first term, if I factored out 4 over n squared from 4 over n squared, I would just be left with a 1. which I'm going to write as 1 squared because 1 squared is the same as 1. From this second term in green here, if you think about 8 over n squared as 2 times 4 over n squared, we can take advantage of some properties of exponents and rewrite this as 2 squared times 4 squared divided by n squared. So 8 over n squared is the same as 2 squared times 4 squared over n squared, which can be rewritten as 2 squared times 4 over n squared. What I'm saying is we can factor out 4 over n squared from this term in green, and what we'd be left with is 2 squared. Similarly, we can factor 4 over n squared from this term in purple. It shows up here in blue, and what would be left would be 3 squared. And we can continue to do that for each of our different terms until we get to this very last term. We factor out the 4 over n squared, and what's left is n squared. We have a ridiculous amount of parentheses and all sorts of craziness going on here, but we have great news. The only ... left here shows up right here. The challenge of this expression is we have n terms. We don't even know how many terms we have, so we kind of can't write the whole expression because of this ... thing. But by doing all this crazy algebraic manipulation, what we've managed to get is 1 squared plus 2 squared plus 3 squared plus ... up to n squared. That's great news. Why? Because at the start of this video, in what feels like ages ago, I presented you this formula that says when you're adding up the square of a bunch of whole numbers up to n, it's exactly equal to this expression, right? We checked it with n equals 4, and I asked you to trust me that it works for all other values of n. What that means is we can replace 1 squared plus 2 squared plus 3 squared all the way up to n squared, what we see right here, with n times n plus 1 times 2n plus 1 over 6. So this huge expression down here, I'm going to recopy it way up top where I have a little bit more room, and I'll be able to use it to figure out this area. So I've taken what's down here and I've copied it exactly up here, except instead of writing this sum with the ... I'm going to copy the right side of this equation. I'm going to write n times n plus 1 times 2n plus 1 divided by 6. The great news is this expression doesn't have this weird ... thing going on anymore. If I could evaluate this limit, I'd figure out the exact area underneath this curve, which is an incredible undertaking. And if you're able to follow it, I am very impressed. How we're going to evaluate this limit? Well, we're going to have to get rid of a whole bunch of parentheses. So let's start over here. N plus 1 times 2n plus 1, if you kind of think FOIL, is 2n squared plus 3n plus 1. If I take this times n, I would get this times n, which is 2n cubed plus 3n squared plus n divided by 6. These parentheses are the same as these parentheses. What about over here? 4 over n squared is the same as 16 over n squared. And 1/4 times 16 over n squared is the same as 4 over n squared. This 4 and one of these 4's cancel, and I get n squared in the denominator. I still have this 3n, and I have to take this 4 over n and distribute it through these parentheses. I don't know if you can tell, but it's starting to get a little bit simpler. If I take this 4 over n and distribute it through, 4 over n times 3n, 4 times 3 gives me 12, and the n on the top and the n on the bottom cancel out. 4 over n times 4 over n squared gives me 16 over n cubed, and that has to get multiplied by 2n cubed plus 3n squared plus n divided by 6. Slowly but surely, I'm getting rid of parentheses. The second to last set of parentheses, these ones right here, I can get rid of by taking this negative 16 over n cubed and distributing it through the parentheses. In the numerator, I'd have 16 times 2n cubed, so 32n cubed, and then 16 times 3n squared, so 48n squared, and then 16 times n, so 16n. And then in the denominator, I would have 6n cubed. Instead of thinking about this as a sum of terms all divided by 6n cubed, I'm going to think about it as 3 different fractions. So I have negative 32n cubed over 6n cubed, and then I have negative 48n squared over 6n cubed, and then I have negative 16n over 6n cubed. I've gotten rid of all of my parentheses except for the last one, this limit. Let me do one more step of algebra and then we'll evaluate this limit. In this term, I got n cubed and I got n cubed, so those can cancel. That leaves me with just 32 over 6, which I can rewrite as 16 over 3. In this term, I can cancel out the 6 with the 48, and that leaves me with an 8 up on the top. And I can cancel 2 of these ends with 2 of these ends. And finally, in this term, 16 and 6 are both even numbers, so I can reduce that to 8 over 3. And I can cancel this end with one of these ends, so I get 3n squared down on the denominator. This might seem like it's really difficult to evaluate, but it's not. Because as n gets really, really large, think like a million or a billion, this gets really close to 0. Right? 8 over a million is damn near 0. The limit as n approaches infinity of 8 over n is equal to 0. So when I'm evaluating this limit, I get 12 minus 16 thirds minus 0 for this term, and then minus 0 for this term, because again, when n gets really large, the denominator gets really, really large. And if you have a fraction where the bottom of that fraction is really large, the value of that fraction gets close to 0. This limit evaluates to just 12 minus 16 thirds. 12 is 36 thirds. 36 thirds minus 16 thirds is equal to 20 thirds. 20 thirds is equal to 6 and 2 thirds, and 6 and 2 thirds is the exact, not approximate, but exact area underneath this curve from 0 to 4. We ballparked that to be between 4.5 and 8.5, which we later improved to be between 4.5 and 7 and 5/8. We originally thought it was, about 6.6, which ended up being a damn good estimation, although not a useful estimation, because this estimation does not translate well to becoming more precise. But this rectangle approximation does translate really well if you can follow the most crazy algebra that you've probably ever seen in your life. If you can imagine n different rectangles under this curve, figure out the width of each rectangle, figure out the height of each rectangle, and come up with an expression that represents the total area of those rectangles, and then do an ungodly amount of algebraic manipulation, taking advantage of this formula, what you end up with is the area of the n rectangles that would approximate the area under the curve is 12 minus 16 thirds minus 8 over n minus 8 over 3n cubed. I'm not going to do it, but if you took this expression right here and you changed all of the n's into 4s, what you would have is the right endpoint approximation with 4 rectangles. You should be able to get 9 halves. I don't want to check it, but you should be able to get there by changing these two n's into 4s. But we don't want 4 rectangles. We want infinitely many rectangles. So we don't change the n's into 4s. We evaluate the limit as n approaches infinity. And doing that allows us to get the exact area underneath the curve. It's not necessarily the calculation or even this absurd algebra that's really that interesting. It's the fact that we can use the same methods we used up here and come up with a formula that represents the area of these rectangles no matter how many rectangles there are. And then we can get super clever and involve limits. So imagine having infinitely many rectangles to get the exact area. That is a brilliant idea that people came up with when they invented this idea of calculus. And it'll be the basis for the rest of our class. Wow.